Now it's time to move past these special cases that we've just done for affine and quadratic functions and just move to the general basis function setup. We'll assume that the approximating function class is given by a basis set, phi1 through phi nb, and the approximating functions are any linear combination of these basis functions using the parameters alpha 1 through alpha nb. With the training set xi, yi, the mismatch at data point I is simply the approximating function evaluated at xi minus the data yi. Substituting the value of the approximating function, which is a linear combination of the basis functions at xi, expresses the error explicitly as a function of alpha. Writing E as an error gives this in matrix vector form. This matrix vector product gives a column vector whose entries are all linear combinations of the alphas. The first entry is linear combinations of the alphas weighted by the basis functions at location 1. The second entry is linear combinations of the alphas weighted by basis function 2, and so on. The ith element of this matrix vector product is exactly that expression. The squared error criterion dictates that we should choose alpha 1 through alpha nb to minimize the norm of E. This results in the least squares problem shown here. This is just a simple generalization of the two special cases that we did in the previous two units involving the affine functions and then the quadratic functions. Here we're just using functions that are linear combinations of a prescribed set of n sub b basis functions. In the previous examples, there were 2 basis functions for the affine case and 3 basis functions for the quadratic case. Here it's more general. There are n sub b specified basis functions. One of the lab assignments is to write this out in general. One of the arguments to the function will be a cell array that contains function handles to all the basis functions.